Hello everyone! I have an acquaintance who is a professional gas welder, by the way, who received his education back in the USSR and worked in serious enterprises in his profession for 30 years. He has been retired for a long time, but he is forced to work, taking on private welding jobs. One day, he approached me with a request to repair some makeshift inverters and to do it as quickly as possible. One of these inverters was repaired the very next day and given back to the person so that the work wouldn't be delayed. The second inverter sat in my warehouse for about a month until I decided what I was going to do with it. Let me say right away, I am not a professional in this field. I don't repair equipment for a living, and I don't charge people for it. I repair at my own risk, and only when close friends or good acquaintances indeed ask me to. In general, my acquaintances know that I never have enough time for anything, so they don't always come to me, to avoid causing inconvenience. I think that's the right approach. There was a time when neighbors, whom I had only seen a couple of times, would break down my door asking me to solder a wire from a cheap phone or headphone charger. Well, you understand you can't live like that, so at some point I started politely refusing. But there are still exceptions. Anyway, getting to the point, the devices that came to me had already been to a repair shop, and the repair cost they quoted the owner was unreasonable. A new device costs even more, so the person came to me. I could have very rapidly repaired the short inverter too, but I decided to film a video so it would be useful for you and I could earn a little from the ads. What kind of inverter, what brand? We'll skip all that. They're all the same, only the names differ. The internals of this unit are quite good. Three-level assembly. At the very bottom is the input section with bridges, a soft start system, and input capacitors. On the middle board is almost the entire power section, the output rectifier, the power toroidal transformer, and on top is the control, the driver, TGR, and current transformer. And also the power bridge keys, that is the inverter, are also soldered onto this board. The device has a classic design. The inverter topology is a full bridge, in my opinion the most reliable, and all sorts of cut-down versions are like something from the devil. The full bridge always rules. The control of the bridge keys is implemented competently and simply through an isolation transformer. A direct advantage of this solution is that if the power bridge transistors blow, high voltage will not reach the control system. I forgot to mention that on the top board we have an auxiliary power supply. This power supply also has a classic circuit design. A single-ended flyback is made based on a current mode PWM controller from the UC family and a powerful N-channel MOSFET. This power supply powers the soft start relays, the cooling fan, and the control system. Apparently, the power supply is around 20 to 30 watts, which is more than enough to power the aforementioned components. What's wrong with this inverter? You might ask. Everything. It's obvious to the naked eye that the power bridge switches blew with smoke. I would say there was likely a small fire here. The input diode rectifiers also burned out, and there are two of them here. Each bridge is rated at 50 amps. How they managed to burn out is unclear, considering the device has a protection circuit breaker. There are two possibilities. Either the bridges were counterfeit from the start, or the technician's negligence led to short circuits. But in any case, it's unclear why everything managed to melt here, and the circuit breaker didn't trip. The device had been repaired before, and the person took it to the same workshop where this inverter was repaired last time. This time they asked for much more money, so the repair didn't happen. Looking at what they did there, it's hard not to curse. The power wires through which high voltage flows were chewed off. Then the damage was wrapped with electrical tape. But the almighty electrical tape didn't save it. Everything here is melted. The explosion was spectacular. I think it's clear what will happen if these wires short with the inverter's casing. And I noticed this blob from the very beginning, and it's a power blob. They probably soldered it with a nail. The bridges are hanging by wires, and this is a factory solution. In the end, the bridges are screwed to the transistor heatsinks. They also lifted the soft start relays. Again, they soldered. It was a nail. As we can see, they didn't even bother to press the relay fully against the board. On the positive side, the inverter is bridge type with good, competent control, a well-thought-out cooling system based on the tunnel principle, massive heat sinks, and a solid transformer wound with Litz wire. The input section is also quite good. They didn't skimp on capacitors, bridges, and relays. In similar devices, they usually put in one relay, one bridge, and at best 4 capacitors of 470 microfarads, but here there are as many as 6. The inverter was used very actively, so the boards are covered with a thick layer of dust mixed with metal powder. I think before starting the repair, it's worth talking a little about the construction of welding inverters and, in general, how a welding inverter works. The presented diagram is purely demonstrative. Any classic welding inverter for manual arc welding consists of several parts. The input part, which consists of a diode rectifier, smoothing capacitors, and a soft start system. A power inverter, which is a pulse step-down power supply with current stabilization. A control system, which in turn consists of a PWM controller and a driver for controlling the inverter keys, a power transformer with an output rectifier, and an auxiliary low-power power source that feeds the soft start relay, cooling fan, and control system. Network. Power is rectified and charges the input capacitors through a current-limiting resistor. The resistor, or thermistor, connected in parallel to the relay contacts, is necessary to limit the charging current of the capacitors at the moment the source is connected to the network. By its nature, a capacitor is a capacitive load, and its charging current is enormous. And considering the number of capacitors in this inverter, if a soft start is excluded, and the capacitors are charged directly, it will trip the circuit breakers and most likely burn out the input rectifiers. The resistor will limit the charging current, and the capacitors will charge to a certain voltage smoothly. As soon as this voltage is sufficient to trigger the auxiliary power source, it will supply power to the control circuit, the fan, and the relay coil. The relays will close, and further power will be supplied to the circuit through the normally closed contacts of the relay. The PWM chip will start generating high-frequency control pulses, which are amplified by the signal repeater and sent to the primary winding of the isolation transformer. This transformer has several secondary windings for controlling the inverter switches. This solution provides isolation of the control system from the high-voltage part. The welding inverter is equipped with a current feedback system. There are many variations of this function, but the essence is the same to ensure a stable current during welding. A simple current stabilization option can be built based on a current transformer. It in turn consists of 2 windings. The primary, usually just a single turn, which is connected in series with the primary winding of the power transformer, and the secondary. The output of the welding inverter is not loaded. The inverter outputs maximum voltage. As soon as the welding process begins, that is, a load appears at the output, the current in the primary circuit increases, and consequently, the voltage on the secondary winding of the current transformer increases. In turn, the secondary winding of the transformer is loaded with a resistor, which is the current sensor. That is, the greater the current, the higher the voltage on the secondary of the current transformer, and the greater the voltage drop across the current sensor. This voltage is rectified and fed through a divider to one of the inputs of the PWM controller's error amplifier. A reference voltage is applied to its other input, which will constantly be compared with the voltage coming from the current sensor. Thus, if the PWM controller sees that the voltage from the current sensor is greater than the reference voltage, it reduces the duration of the control pulses, thereby causing the power transistors to open for less time, and consequently, less power goes to the power transformer, and less power is at the output. This process occurs constantly thousands of times per second. Thus, the inverter tries to maintain the output current at the level you have set. Now let's get to it. The repair will not be quite standard, or rather, it will be standard but comprehensive, and therefore, to begin with, I completely disassemble the inverter. After disassembly, we once again admire the control board and the traces of a mini explosion. Well, I don't see a more reasonable way than to wash this board in the shower. We take a toothbrush and thoroughly remove all the dirt from both the component side and the trace side. After the shower, we send the board to dry at a temperature of about 40 to 50 degrees. I don't have a bottom heater, so I use regular heating radiators, but I dry it for several hours. After these few hours, we throw the board on the table for diagnostics. First, we check the bridge keys, and it seems like half of the transistors are for scrap. Since the repair is on my dime, we desolder all the keys. It is highly advisable in such cases to replace all the keys and use transistors from the same batch. By the way, the keys here are quite good K30A603, not from just anyone, but from Infineon. And these things aren't cheap. I'm even afraid to imagine how much the local vendors will ask for original keys of this kind. At this point, it's unfair to blame the workshop for the exorbitant cost of the repair. In mediocre stores, such keys cost 250 rubles, and here they are 350 each. 8 keys, that's 2,800 just for the keys. Plus the cost of the repair, plus some minor work, maybe something else burned out, plus cleaning, blowing, and we're getting close to the mentioned 5,000. That's exactly how much they asked for the repair of this device. For that kind of money, you could buy a mediocre new inverter. But on the other hand, it's clear how this amount adds up, considering the price of parts and the fact that the client always wants to do it cheaper, while the technician won't work for free and values their time. But in this particular situation, I'm on the client's side. If the technician is going to repair it so carelessly, then it's better not to. There are 8 keys here. Each pair is parallel to increase the total switching current and to ease the thermal conditions. We take a powerful soldering iron with a wide tip and desolder all the keys. We do this after thoroughly heating all 3 leads of the keys and carefully pull the transistor to avoid tearing the metallization. That's it, the keys are out. Now you can check everything again, discard the faulty ones, and keep the working ones for DIY projects. But if you do this professionally and charge for it, you should return both the working and burnt-out keys to the client. Next, I tested some components in the control system. Specifically, the galvanic isolation transformer GIT has 5 windings. 4 of them are similar and control the gates. Of the bridge keys, we thoroughly check all the gate windings for any breaks. Then we check the gate circuitry, which is soldered on the board near the gate. I didn't notice any anomalies here, but everything will become clear during the final diagnostics, when using the oscilloscope. I also tested all the gate resistors of the bridge keys. They are all at 4 and 7 ohms, but there is a noticeable variation in resistance, so we are replacing all of them. Next, we carefully inspect the large control board for any suspicious components, swollen capacitors, the presence of scale on components, as well as the formation of ring cracks on the pads. If you look at the vertical board with the PWM chip, seems like there are oxides or some kind of residue. In general, I cleaned everything with solvent and additionally resoldered it. We do the same with other suspicious and semi-suspicious areas. Now we need to start the control system. You can supply power from an external source like a laboratory power supply, but here the auxiliary source, like a standby power, generates several secondary voltages, so it's better to start it right away. If you look at the board, you can notice the technological jumper with a blob of solder. This is the power input plus. By breaking this jumper, we disconnect the plus 310 volts for the standby from the main hot input. But in this case, it can be left as is since all power is turned off. But still. And the outermost contact is the high voltage minus. You need to apply about 310 volts of DC to these leads through a safety current limiting network lamp of 15 watts. For these purposes, I have a quickly made gadget. A bridge, a capacitor, and a thermistor. Mains voltage is applied to the input, and the output is about 310 volts of DC. We apply power to the standby input and probe the gates of all 8 switches with an oscilloscope, observing a similar pattern. I don't see any significant deviations. Dead time is clearly observed. The signal is clear and beautiful. At this stage, this board can be said to be working as it should. But that's not certain. The operation of the feedback is still in question. Of course, it can also be tested by, for example, supplying power from an additional source to the load resistor, which is also the current sensor. But that would confuse you more, so we'll perform the test on the assembled device at the very end. In the meantime, take a toothpick or a desoldering pump and carefully clean the mounting holes of the bridge keys from solder. That is, we prepare the board for installing new transistors, and then set it aside, and proceed to restore the input board. On this board, we have storage capacitors, a couple of 50 amp bridges with protruding wires, and a couple of relays. There was also a 5-set thermistor in the soft start circuit, which conveniently fell off during disassembly. I have a choice, to make a new board or to restore this one. It's basically fine, except for the traces of someone's mischievous hands, but that's fixable. What I don't like the most is the execution of this board. A couple of bridges are just sticking out with wires. That's not cool. And honestly, I almost designed a new board, and even wanted to order it, but an acquaintance hurried me with the repair, so I had to restore this board. Initially, I desoldered almost everything, checked the capacitance of the capacitors, their internal resistance, and also checked the relays. Everything seems to be fine, except for two 50 amp diode bridges. Both are scrap. I have counterfeit KBPC 50, 10 bridges. I also have these also rated for 50 amps, 1 kilovolt. They can easily handle currents up to 30 amps, maybe more, but I haven't tested it. In general, 2 of these bridges will be more than enough. Next, the board was cleaned, all components were soldered, the traces were restored, and the power wires were replaced. By the way, I won't be mounting the bridges on terminals, I'll solder them. It's much more reliable this way. But of course, don't forget about the thermal paste. After restoring and cleaning, I coated the board with 3 layers of varnish on the trace side and lightly glued the capacitors. Perhaps the most tedious process was dealing with the wires. The original wires with connectors were discarded because they were melted. The problem is that I don't have such connecting wires, let's say ribbon cables, and getting them is practically impossible without radio stores in our area. In the end, I just drilled new holes, made all the connections not with connectors, but simply soldered them. It's more reliable this way, and in the future, this modification can be removed and everything can be returned to how it was. All of this was previously agreed upon with the owner, but I still had to make one power harness from what was available. By the way, near the leads of some transistors, burn marks are clearly visible. The fiberglass in this area is blackened, and it is essential to mill it down to clean fiberglass and then cover it with several layers of varnish. I simply blew out and cleaned the power board with the heat sinks, output rectifier, and transformer. The thermal paste under the diodes, of which there are 8, is in good condition and didn't need replacing. And finally, there's something to be decided with the bridge transistors. I have a lot of cool original IGBTs that a kind subscriber sent me, but there's a nuance. This inverter operates at frequencies around 30 kHz, give or take, and the transistors need to be chosen carefully if you don't have the ones originally installed at the factory. You need to primarily look at the current and the maximum voltage of the switch, and also, importantly, the turn-on and turn-off times, especially the latter. The smaller these parameters, the faster the transistors can operate at high frequencies. Many manufacturers do not specify the operating frequency of IGBTs, but knowing all these parameters, you can roughly estimate at what frequencies the transistor can operate. The characteristics of the internal diode are also important. It also has specific turn-on and turn-off times and voltage drop. It is also worth looking at some graphs and comparing them with the graphs of the transistors that were originally installed. This particular point is important, the dependence of the switching current on frequency. No matter how advanced the transistor is, it has limitations. Even if the switch is rated for 100 amps, note that as the frequency increases, the switching current will be lower. And this is a very important parameter when selecting equivalents. The saturation voltage collector emitter, the lower the better. This parameter shows the voltage drop across the transistor junction, and is comparable to the on-resistance parameter in the case of field effect transistors. The lower the voltage, the less the transistor heats up. Regarding my transistors, although they are cool, for most of them, frequencies of 30–40 kHz are the limit. And even then, at such frequencies, their switching currents are not great. There's also the option to use 4 surviving switches, 1 for each leg. In that case, the maximum output current of the inverter would have to be reduced. But we're doing it the right way. Here are the switches I'll be using. 60N 6060 amps, 600 volts. They are very often used in welding equipment, overall a good option. They were bought from vendors who swore they are original. Appearances can be deceiving, but most likely it's either a super high quality fake, or actually the original. All dimensions match the technical documentation, as do the main parameters. But whether they have the right crystal inside, you can't say until you test them or break them. It's a shame to break them, after all they are expensive. At the very beginning, I soldered only 4 keys so that in case of anything, the loss would be minimal. The thermal pads under the keys were in poor condition, so I replaced them as well. After that, I assembled everything together and ran the device in a semi-assembled state at a current of 60 to 80 amps. I made sure everything was fine. Then I soldered the remaining 4 bridge keys and assembled everything completely. Beforehand, heat shrink tubing was applied to the transistor leads for insulation, and this process is highly recommended. The first start of the device should be done through a safety network lamp of 150 to 300 watts, which is highly recommended to be connected after the main capacitors, as their capacity is enough to burn out the entire circuit if something is wrong, and a lamp at the input won't save it in that case. Well, it's better to supply not the full network power, but a reduced one from a variac, gradually increasing the voltage. After making sure that the system is working properly, it is necessary to check the operation of the current feedback. Under no circumstances should you short the inverter output directly. If there are problems with the feedback, the current will not be limited, and the power transistors will simply explode. I load the inverter with a ballast of 1 ohm resistance. Considering the inverter's output voltage according to Ohm's law, a current of about 80 amps will flow through the ballast, no more. Now regarding the test. The device is connected to the network through a wattmeter. The power consumed from the network is about 160 watts at idle. The open circuit voltage is 80 volts. This is more than enough for a good arc ignition. The device is loaded with a ballast. The load current is 100 amps. The consumption from the network is 16 amps. I forgot to show, but the voltage in the network dropped to 200 volts due to the use of a 20-meter extension cord. The output voltage of the device is 24 volts. The efficiency is about 75%. But considering the losses in the wires, the efficiency would be higher. The minimum output current of the device is 20 amps. I reduced the current to 140 amps, although the device could easily deliver 200 amps, but I'm not sure about the transistors, and besides, this decision will clearly extend the life of the device. The owner approved this. Now let's try with a 3mm electrode. I set the current to about 120 amps, whether it welds well or not. Whether the arc flows easily or not, I don't know, I'm not a welder and can't fully convey the feeling to you. The device is just a device, it welds fine. I burned through a few electrodes, and during this time the device didn't explode, didn't overheat, and overall everything seems fine. What can I say in conclusion? I have a welding inverter, and not just one. I have a few homemade ones, but I somehow never have enough time to learn welding. So, if my inverter had burned out, honestly, I wouldn't have bothered with repairing it. We breathed new life into the device, and I hope it will serve its owner reliably for many years. That's all from me. Rate this long and tedious video, which for many was about nothing at all. Well, that's probably it. You'll find many useful links in the description. Well, with that I say goodbye. As always, this was Kazyanov K, with you. Until next time, bye.